So I'm going to work through problem number 5 for the final exam for fall 2010. And in this particular problem, it defines a function f of x as equaling to the square root of 2x plus 1 minus 3 divided by x minus 4 when x doesn't equal to 0, and f of x is equal to 0 when x doesn't equal to 4, and then so f of x is equal to 0 when x equals to 4. So basically, we're talking about we're going to be using this part of the function whenever from minus infinity to 4, and then from 4 to infinity, and we're going to be using the domain of this is going to be whenever x is equal to 4. And so it's asking us to find the limit as x approaches 4 of f of x. So again, when you think about a limit, you need to think about, does the function approach some value at a given x from the right and from the left, and is that value the same? So the limit basically says that if you have some limit as x approaches a from the right of a function, if that limit is equal to the limit as x approaches a, that same value, x value at a from the left, if this condition is true, then you have the limit. You have a limit L at x is equal to a. Okay? Now, what this is actually meaning is that if we have some function, and let's say that this function here is represents this part of the complex function. So this is going to be a, and this part of the function is going to be b. Okay, so this is going to be a. So for the a part of the function, let's say it looks something like this. Because at x is equal to, and let's say that this point here is x is equal to 4. And we know that if this function, it's not defined at 4. So we put a hole there. But you see that as we approach x is equal to 4 from the left, it basically has some y value. Okay, some y value is equal to c. And if we approach x equal to 4 from the right, we see that the function is still approaching that same value from the right. And so if we had this particular function, if this was our function, we would say that even though that there's a hole at x equals to 4, the limit still exists at this value y is equal to c, because the function is approaching the same value from the right and from the left. And so let's say that we had x equal to 4, so this is b, this represents b. Even though that at x equal to 4, our value is actually 0. So this is y is equal to 0 here. Okay, and this is x is equal to 4. So this is x is equal to 0 here. The y value at x is equal to 0, they tell us, is 0. So if we have this situation where we have a and b, we know that the limit of this function is actually going to be whatever this y value is, because we don't care that it's jumping here. We just want to know what the function is doing as it approaches 4, and it looks like that is going to equal to some value y is equal to c from the right and from the left. Okay, so you have to understand that in order for you to work through this problem. And so knowing that, we want to see what's happening to the function as x is approaching 4, so we're talking about not when x is equal to 4, so we're not worried about this. We want to know what's happening as it's approaching 4, so we're going to look at this particular part of the function. So we're going to take the limit as x approaches 4 from the right, and we're going to take the limit as x approaches 4 from the left of f of x. And we're going to get some value, limit 1, okay? And for this one, we're going to get a different limit, L2, L sub 2. And if these two are equal, okay, then that is our limit, L, okay? If we take the limit as x approaches 4 from the right and from the left, and we get some L1 and some L2 such that both of them are equal, then the limit as x approaches 4 of f of x is just equal to that L, okay, which is also equal to L1, which is also equal to L2. All right, so we need to see if we're going to get this condition where the right, as we're approaching 4 from the right and from the left, are going to be the same, the limit. Okay, so let's do that. Let's take the limit as x approaches 4 from the right of the square root of 2x plus 1 minus 3 divided by x minus 4. And we get direct substitution, limit as x approaches 4 from the right of 2 times some number that's not equal to 4 but slightly bigger than 4. So I use the notation 4 superscript plus that denotes some number greater than 4. Okay, so this is how I would write it with direct substitution, some number slightly larger than 4. So that, and when we evaluate this, is the limit as x approaches 4 from the right. When we do the math inside here, we get 2 times 4, which is 8, plus 1, which is 9. The square root of 9 is 3, but it's going to be a number slightly greater than 3. Subtract 3, so we're going to get a number slightly greater than 0, but really close to 0. And on the bottom, we're going to get the same thing, a number that's slightly greater than 0, but pretty close to 0. And that final result is going to be positive, some positive number, okay? Let's do the same thing now, but we're going to take the limit as x approaches 4 from the left. So we get 2x plus 1, the square root of that, minus 3 divided by x minus 4. Doing direct substitution as x approaches 4 from the left, we get 2 times 4, a number slightly less than 4 this time. We take a square root of that, subtract 3, and then we have 4 minus 4, a number slightly less than 4 minus 4. This is just substituting in a number that's slightly less than 4 but really close to 4. And we get the limit as x approaches 4 from the left. In this particular situation, we're going to get 0 over 0 again. But this number is going to be, again, a negative number, and a negative number is still going to give us a positive number. And these two positive numbers are going to be basically the same. Okay? All right. So, we still haven't solved the problem. We got 0 over 0. We know that it's going to be positive. But when we get 0 over 0, we know that's an indeterminate form. So these are indeterminate form. If we plugged in x is equal to 4, we would get exactly 0 over 0, which would be an indeterminate form. Okay, so What does that mean? That means that we can take L'Hopital's rule. So we take the L'Hopital's rule says that we can take, as x approaches a, of f of x is equal to either 0 over 0 or plus or minus infinity over infinity, that we can basically say that that's the same thing as the limit as x approaches a of the derivative of f of x over the derivative of g of x. This should be a g of x here. Okay, so the limit as x approaches a f of x over g of x is equal to 0, 0, or plus or minus infinity over infinity, then we can rewrite that limit just taking the derivative of f and taking the derivative of g and dividing them. So if we define our f, in this particular case, to be the square root of 2x plus 1 minus 3, and our g to be x minus 4, then the derivative of f is just simply 1/2 times 2x plus 1 to the negative 1/2 times the derivative of the inside, which is just 2. And I can cancel out the 2's. So rearranging this, this will just be 1 over 2x plus 1 to the positive 1/2, and that's the derivative of f. The derivative of g is just simply 1. Okay, so we can rewrite our limit as x approaches 4 from the right, and our limit as x approaches 4 from the left. Remember, we're still trying to evaluate what's happening from the right and from the left. And so now we're going to use the derivative. The derivative is 1 over 2x plus 1, the square root of that, or to the half. And that's going to be divided by our derivative of g, which is just 1. And this is going to be the same thing. Okay, so these are our new limits as we're approaching 4 from the right and 4 from the left. And we can evaluate these limits by putting in a number slightly greater than 4. Okay, so in this particular one, all I did was substitute in a number that's slightly greater than 4 in for x, and I substituted in a number that's slightly less than 4 in for x in this particular limit. And when we evaluate this, we're going to get 1 over 2 times 4 is 8 plus 1 is 9. The square root of that is 3, but it's going to be slightly greater than 3. So the answer is going to be 1 over 3. We know it's positive, and it's going to be some number slightly greater than 3. Some number slightly greater than 1/3. But essentially, this limit is approaching. So essentially, it's approaching. It's approaching 1/3, because this number is really, really, really close to 1/3. So the function is essentially approaching 1/3 from the right. Now, when we evaluate the limit from the left, we're going to get the same thing, except for we're going to get a number that's still positive 1/3, but it's going to be slightly less than 1/3. But essentially, it's approaching positive 1/3. Okay, so we can see that this limit, which we call L1, is equal to L2. These two are equal, and so that's equal to our limit L, which is just 1/3. Okay, and that's the answer, is 1/3. Now, you say, sorry, you say, wow, you know, that's kind of a lot to do. Couldn't I just, you know, take the limit of as x approaches 4 of f of x? So if you do that, okay, this function is telling you at x is equal to 4, f of x is equal to 0. So the limit, if you just go directly from evaluating this limit, you would have to say f of x is equal to 0. But you don't want to know what's actually happening at x is equal to 4. You want to know what the function is doing as you're approaching x is equal to 4 from the right and from the left. That's the reason why we had to look at this limit of what's happening when x is approaching 4 from the right and from the left. Also, so the answer is 1/3. I just want to kind of make some notes here to hopefully clarify everything. You also, you would say, okay, well, if I plug in 4 on the denominator, I would get 0, and we know that if we get 0 in the denominator, then you should have a discontinuity of the function, right? But if we actually look at the graph of this function, it actually looks something like this. Which is what I drew earlier. Okay, so this is basically that's what this is. Okay, so this is f of x. All right. All right. So why do we, if we just ignore the conditions here and just plot this function, you would get something that looks like this. And you would ask yourself why, so this would be at x is equal to 4, okay? Then you would say, well, why don't I get a whole at x is equal to 4? Okay, why don't I get a whole at x equal to 4? Because if I put 4 in the denominator, I'm going to get 0. Well, that's because you have to basically try to see if, you would think you would get a vertical asymptote at x is equal to, at x not a whole, a vertical asymptote at x is equal to 4. But actually the definition of a vertical asymptote is if you take the limit as x approaches some value a of f of x, and that gives you plus or minus infinity, then you have a vertical asymptote. Okay? Or if you take the limit as x approaches a from the right or the left of f of x, and you get plus or minus infinity, either one of those conditions are going to give you a vertical asymptote. Okay? Vertical asymptote is not defined by if you get 0 on the denominator of a fraction. A vertical asymptote is you need to take the limit of the function as x approaches some value, and if that gives you plus or minus infinity, then that is a vertical asymptote. And you can see that even though that we get 0 on the bottom here, if we take the limit of this as x approaches 4, if we actually do that, you'll see that you won't get plus or minus infinity. So let's do that. let's take the limit as x approaches 4 of f of x. And f of x in this particular case will be this one. So this 2x plus 1, the square root of that, minus 3 divided by x minus 4. And if you will put in direct substitution, you would get the limit as x approaches 4 of you would get this for direct substitution, and this would just be 3 minus 3, which is 0, and this would be 4 minus 4, which would be 0, which would give you indeterminate form. Okay? That's if we were taking the limit of this. Okay, we're taking the limit of this. We're not taking the limit of this function. This is not the function, because if we were to take the limit of this f of x as x approaches 4, we would have to say, and we're substituting in 4 itself, that would just be 0. But we're taking the limit of this one, so that would give us indeterminate form. And again, you could take the derivative. So if I define f of x is equal to 2x plus 1, the square root of that, minus 3, and g of x is equal to x minus 4, then the derivative of f is just going to be 1 over 2x plus 1, and g of x, the derivative of g is just going to be 1. Okay? And if we now take the limit as x approaches 4 of 1 over 2x plus 1 to the half divided by g of x, which is just 1, and we do direct substitution, you'll see that you'll get 1/3. Okay? And so basically what this is saying is, as you approach 4, as you approach this function, as you approach 4, this function, as you're approaching 4, you're going to get, the limit is going to be, the value of that function is going to be 1/3 as you approach 4. Okay, so hopefully that's a little bit more clear. The reason why we couldn't do this at the very beginning is because our function is defined to be 0 at x is equal to 4. And so the limit of, let's say, so in the very beginning we had the limit as x approaches 4. If we're going to plug 4 in of 0 is just 0. But this wouldn't have been the correct answer, because we don't care what's actually happening at 4. We care as it's approaching 4, and so we want to take the limit. We want to do this here. So this is another way we could have done it. That basically is consolidating what we did initially by looking at what's happening to the limit as you approach 4 from the right and from the left.